Alright, so this is homework 3 part B, and we're going to go over the Nusselt number and how convective heat transfer over a plate with laminar flow follows that equation, and how to maximize heat transfer over a rectangular plate. So the equation, let's rewrite it. It's Nusselt number in the x direction. We're only thinking about this in the x direction. 0.332 Reynolds number to the second times over 1/3. So let's write out each dimensionless number in its units first. So Nusselt's number is convective heat transfer. Over conductive heat transfer. Which translates to H x over thermoconductivity. Reynolds number is density over density times velocity in the x direction over viscosity, and Prudence number is momentum diffusivity. Over thermodiffusivity. Which is viscosity divided by the density over heat conductivity divided by heat capacity times density, which simplifies to rho times the heat capacity over thermoconductivity. So now let's draw the rectangular plane and model what flow looks like. So here's the plane. So the flow is going this way, causing the flow is going this way. So once the flow hits, it causes it to go in the upward direction, causing these to slow down once it hits it. So This distance is called x. And the disturbance of the slowing goes in that direction. It keeps increasing as the further the x goes. Distance is called sigma. Alright, so now let's plug these equations into this, or the into that equation to see how to maximize heat transfer over a rectangular plate. So Nusselt's number is equal to 0.332 times Reynolds number, which we said was density times velocity times x over viscosity times Prudence number, which was viscosity times the heat capacity over thermoconductivity. This is up to the third, power to the third, and power 1/2. Alright, so now let's solve for h. And now let's simplify. So after simplifying, what stands out to me is the x. So the distance, if you were to decrease x, h would increase.